So let us conclude this session about dynamical system, speaking of what I think is the most important and interesting topics. It means chaos. Actually, I wrote here low-dimensional chaos because this is chaos in the sense of dynamical system. I mean, systems defined by few equations of motion, while we shall meet in the following another view of chaos. I mean, chaos in a system composed by a very large number of, say, interacting particles and so on. Okay, so let us start with an experimental setup that you can try to reproduce. This is essentially a water wheel, but while in general water wheel are made in such a way so to turn always in a certain direction, this has been specifically designed in order to be as symmetric as possible so that it can turn easily in both directions. You see that each of these glasses have a little hole at the end so that they lose, say, water. They are not like in a standard water wheel where the water is released in the lower position. And you can notice that actually it turns for a certain amount of time in one direction, then turns back, and so on. And so we would like to simulate the same thing using okay, first NetLogo and to study what happened. If you are interested, there is a complete treatment of a continuous or mostly continuous version of this water wheel on the Strogatz book and nonlinear dynamics and chaos. So here is essentially the setup, and this is a typical time series of the angle. So you see that this is of the velocity of the angular speed. So you see that it goes, so it is positive, so it turns in one direction, even though with acceleration here almost stops, and then at this point it turns back because this is negative, and again and again. Okay, so let's have a look at what we can do with NetLogo. The interface is essentially this one, so that you have set up, go, you can set parameters, but essentially what is interesting here is that I did the simulation using two two copies of the same system, so that you can have a look at not only to the position, here is the position of the center of mass, but also on the difference of two almost identical, so the system are identical, but they start with a very, very small tilt one with respect to the other. And so this is our interface here. You see very small red dots, which are the buckets, the glasses here, and when they fill with water, they start to grow. So we can go slower. So they start almost in the upper position, so that the system is very near to an unstable fixed point. And so after a certain time, you see here the position of the center of mass of the system with respect to the center. After a certain time, it goes down. Only the bucket, the glass that is in the upper position is get filled. So you see that you have a certain oscillation. Here you see the trajectories of the center of mass, and here the time series. I told that they started with very different, slightly different initial conditions, and so you see that after some time, the two wheels are now turning in the opposite direction. Sometimes they start again to turn in the same direction, and so on. So they separate completely. Notice that if you repeat this simulation, you have to to put a certain amount of friction, otherwise you don't see this behavior. Notice also the shape of the trajectory marked by this central point. We can redo it in a faster way. So you see that actually the center of mass turns a bit around, say, one of these 2 points, and then around the other, and again around the first, and so on. Okay, so let's back to the presentation, and actually this we shall see that this model is very similar to an older one, the Lorentz model, that was studied by Lorentz, who is, I think it is still alive, a meteorologist in the 60s, I think in 1963. And the Lorentz model is a very simple schematization of the atmospheric convection, or of the convection in a slab with a very one-dimensional aspect ratio. And actually it is a truncation at the first order of the Fourier series. So I also worked when I was young on an experiment like this. So essentially you can take a rectangular container, you heat it from below. Since water is, or any fluid in general, is lighter when it is warm, so there is an instability. At a certain point, for very small temperature difference from top to bottom, the liquid start to form these rolls and transport energy from from the bottom to the top. And the Lorentz model, I don't derive here the Lorentz model, but it is essentially described by this set of three equations. Clearly, since we are going to model chaos, we need at least three equations, because chaos means that nearby trajectory tend to diverge, to separate, but globally they remain confined in a certain region. And clearly, for a one-dimensional system, you cannot have something like this if it doesn't go into a stable fixed point. For two-dimensional system, you can only have, say again, stable fixed point or limit cycle, but in both cases, you don't have a divergence of trajectory. And only in three dimensions, trajectory can avoid and separate, clearly for a relative finite amount of time, still being confined in a certain region. Okay, so these are the equations. You see that they are almost linear. I mean, there are some quadratic nonlinearity here and here. For the rest, the model is linear. And actually, if you go to the Strogatz book and see the derivation of the equation of motion for the chaotic water wheel, the first equation is linear in both models. You see that after proper rescaling of variables, you get the same equation. The second one has this quadratic nonlinearity here that corresponds to this one. Then this term is similar to this one. Clearly, we have a constant term, and here you have this other term. So they are not exactly the same, but the structure is very similar. While the third term does not have this quadratic nonlinearity here, but okay. So essentially, it is both are systems that are almost linear with quadratic nonlinearities. So Lawrence started to study this equation by hand. You can easily see that there is a fixed point in the origin, 0, 0, 0. If you substitute, you have 0, so it is a fixed point. And so, for instance, by changing r, you can study the bifurcation. If r is greater than 1, the origin becomes unstable. There is a saddle, so this becomes unstable, and two other fixed points appear. They correspond essentially to rolls turning in one direction or in the other direction. And but he was able to demonstrate that for further values of R, these two fixed points become unstable. It appears a limit cycle which is unstable and separates. So essentially, here you have a spiraling towards this one. Here you have exponential growth of this circular motion, but he was not able to find any other known attractor, essentially any other cycle or fixed point. So he decided to use a computer. Now, the computer at that time was something like this. I mean, with a printer, which was essentially a teletype, something to type down the program code, no graphical screen, and the computer itself was built using valves, so often he had to be repaired by some technician. When I say that Lawrence started to watch the trajectory, I mean that he was actually reporting on a sheet of paper all the numbers that were teletyped by the computer. So actually these are some of the original drawing by Lawrence. And so you can see what happens here, that as I said, there is no recognized say cycle or something like this. So he decided at a certain point to go on to make a larger simulation. Maybe this was just a transient. And so instead of starting from the last point, he, in order to check also the fact that the computer was working in the right way, started by inserting, say, the number here. And clearly the simulation continues to reproduce what was already done, but at a certain point you see that the red trajectory goes in a completely different path with respect to the blue one. Clearly they stay always inside the attractor, but they were completely different. So the first thing that Lawrence thought was that the computer was broken, so he called the technician. They revised everything, and nothing was found. And finally, he had to accept that he had discovered something new. Chaos. I mean, the fact that two trajectories can can separate, still remaining inside the same attractor, and by plotting the trajectory in the x, y, z plane, you find this wonderful attractor that we can also reproduce this time by using NetLogo 3D, because clearly it is in 3 dimensions, so it is much better appreciated in 3 dimensions. And so let's load this 3-dimensional Lorentz model, which is something which is slightly more heavier than the usual one. Let me see if I'm able to put it all together on this other screen. Maybe I may reduce a bit the dimension here. this is a different view. Here you can see. So actually in the 3D version, this is the space and this is the front end. So we can set up the system with just a single turtle, let it go, and as you can see, this turtle draws the attractor. Now we can explore and turn it from several point of view. You can see that this attractor is formed by two almost flat wings or leaves, and these are, when you see it perpendicularly, these are almost flat. You may recognize the unstable point here in the center of these two leaves. These are the C1, C2 dot unstable point, spiraling unstable point that we have seen before, and so we can clear trajectories and go again, and you see that what is going on is that the trajectory turns for a certain amount of time around one of these points, then jumps on the other, and so on. And in the middle, you can see that there are trajectories that you see here. Some of them goes into the other leaves, some of them comes back to the same wing of leaf here, and we can also do something. I mean, clone the system, and now we have two turtles that the cloning has occurred with a very, very small difference in position. So essentially we are repeating the Lorentz experiment, and this is, here is the plot of the difference, the distance between the two trajectories, that maybe we can clear trajectories, or maybe we can start again and let go for some point. Then I clear trajectory, I clone the system, and then I let them go. And you see now that everything is white because they stay in the same position. Then at a certain point they separate. Maybe we can do it again. Clear trajectory, let go slower, go, even slower, and so you see that we just see one trajectory, and then at a certain point I reproduce. Now we have a green and a white one. They stay together, so the difference is 0. But you'll see that at a certain point one of them will separate. One probably will go from one in one wing and the other in the other one. So they still stay together, even though there is a small difference between these two. Again, they are still together, and now they are starting to really separate, and maybe we can clear again the trajectory. And now you see that one of them has went in the completely different direction. So one is turning here and the other here. Sometimes they join together and the distance goes to 0. Sometimes they separate again, and so on. Okay. So this is the Lorentz experiment, and we have to quantify, for instance, how this separation occurs. So the idea is to try to compute analytically, or say using computers, the direction. Clearly, the difference between two trajectories. What happens in a stable system is that this difference goes to zero. If they go into a stable, in a fixed point, this difference goes to zero. If they stay in a limit cycle, this difference can oscillate, but essentially it is limited. Also, in a quasi-periodic motion, nothing very similar occurs, and but in chaotic system, this amplifies. So these two trajectories, let us, for instance, perform the analysis for one-dimensional system in which there is no chaos, but we can develop the terms. You can call these two trajectory x and y, and since they start very near one to the other, we can develop linearly the system as before. And so the difference here in the absolute value behaves like this. So you can see that developing at first order, it is again the derivatives that counts. But while in a one-dimensional system you have computed the derivative in a fixed point, here we are now computing the derivative on a trajectory, which is essentially the same, because also fixed point is a kind of trajectory. So by, say, reformulating the system using discrete time step, we shall now at the end take the limit delta t equal to 0. We have this equation. So actually now we cannot simply take the power of this, because this is something that changes along the trajectory. So what we do is to take the product of all this contribution in order to arrive from delta 0 to time 0 to time n, and in terms of delta t. Clearly, it is instead of dealing with the product, we take the exponential, so we are now dealing with a sum. And this is the sum, and the limit delta t equal to 0, the logarithm of 1 plus something small becomes just this quantity here. And so essentially we can define a Lyapunov exponent, which is the temporal average of the derivative of the function. Clearly, this is something which is corresponds to what happens in limit cycle, where this is constant. So essentially, the average is just the value of the derivative. Clearly, if lambda is greater than 0, the trajectory diverges. And so this is the essence of chaos. However, in 1 or 2D, we cannot have chaos due to the fact that the trajectories are not confined. So for autonomous system, clearly for non-autonomous system, it is as if we had other dimension due to the forcing. So we may have say chaotic system also in 1 2D, for if the force depends on time, for instance in the forced pendulum or something like this. And for studying the problem in at least a 3 dimension, we have to reformulate the equation in vectorial terms. And so we have to now consider the Jacobian of the system, since delta evolves as the Jacobian, and we have to redo the same analysis, similar analysis using A, which is 1 plus the Jacobian times delta t. Then we have to study the geometric mean of A of t, but as usual, it is much better to introduce the eigenvalues of the geometric average. And so these are the eigenvalues of this product of matrices. And so if we iterate enough, clearly the average at a certain point it does not change a lot. So it is like as if we iterate the average to the power t. And so clearly, since we have ordered the eigenvalues this actually is the absolute values of the eigenvalues. Here there is an error, and the largest one dominates. All the others can be disregarded. So essentially, we see that if we take an initial vector and we iterate it along the trajectory, at a certain point, all for any initial direction, they all points in the same direction, which is the direction corresponding to the eigenvector that corresponds to the largest eigenvalue. And clearly, in order to obtain the other eigenvalues, we have to carry with the point a number of orthogonal vectors, so that one, say this one, aligns in the direction of the maximum expansion. The other may rotate but stay perpendicular to the first one. So the second aligns with the second eigenvalues, those corresponding to the second eigenvectors that corresponding to the second eigenvalue, and so on. And clearly, we have the logarithm of these things, since they are the logarithm of something 1 plus the Jacobian delta t. We can do exactly the same, and the relationships between alpha and lambda is that lambda is the logarithm of these of the eigenvalues of this one divided by delta t. So in practice, what we shall do in the computation is we have to take a reference point, one point that follows the trajectory. Then, instead of doing, as we have done theoretically, manipulation of derivatives now, because this depends also on the numeric algorithm that one uses to compute the evolution of the system. So it is much better to take a certain number of vectors, starting, say, with some small quantity. The norm is some small quantity. Then we iterate this number of, say, we compute the new coordinates, taking the coordinates of the reference point and summing these small vectors. We iterate y for a small amount of time, and we take the difference with respect to the evoluted position of the reference point, and so now we have new values delta after some time. Then, using Gram-Schmidt or other technique, so these vectors started like this with respect to the reference point. Suppose that I started with a certain amount of a certain number of vectors like this, perpendicular to each other, with respect to the reference point of my system, and this evolves for a small amount of time. These three vectors tend to align, let's suppose this like this, tend to align to the most expanding direction, like this. Now, and they change their sides. Now, because this is expanding, maybe the others are contracting, say. So, when we normalize the first, I have an estimation of the first Lyapunov exponent. Then I orthogonalize the other with respect to this, for instance, the second. Then I recast the sides to the original sides, and so I have an information if the second eigenvalue is expanding or contracting. Then I do the same for the third, and so on. And so, by normalizing, first orthogonalizing and then normalizing them, I get the how their norm shrunk or expanded according to the amount of time, and then I accumulated the logarithm of this variation of the norm. Clearly, since I started with Q, I have to rescale the new norm with Q. I divide by delta T, I divide by the number of times that I accumulated quantity, and in this way I get the Lyapunov exponent. So before going to the simulations, let's check, so let's have an expectation of what we should see. Clearly, there is a very strong contracting direction perpendicular to these leaves. Clearly, it is not constant, the direction changes with evolution. Because I need this strong contracting direction, because I saw that all initial points very quickly go on these almost one two-dimensional leads. So I expect that there is a very strong contracting direction perpendicular to the wings of this butterfly. Then from the shape itself of the trajectory, you see that in this direction we don't have any contraction, because essentially you see that the trajectory stays near one to the other, turning around. If there were a contraction, there will be a limit cycle. If an expansion, there will separate. And so the separation of trajectory is in this direction. Along the trajectory, they tend to separate it, so that at a certain point one goes in this on this wing and the other stays on this one. So essentially, now I am plotting the direction of the three reference vectors with respect to the reference point. So you see that these are the green, red, and blue correspond to these three Lyapunov exponents. So you see that the blue actually is strongly contracting to this. Is the factor of the exponential, and you see that the red one is on the plane. Clearly, it is a direction, so it may go towards the direction of the motion, or in the opposite direction. Maybe if we start again, sometimes it goes in the right direction. No, this time maybe. Okay, now it is oriented in the right direction. So we can see that the red one is on the plane here, in the direction of motion, while here, while the green one is still on the plane of the wing, but perpendicular to the direction of motion. And the blue one is essentially perpendicular to the wing, and you see, and if you compute all this expansion of the here of the computation, you get these three numbers. Clearly, one should then say iterate for a long time. So let's go faster in order to have an idea of where these numbers are going to go. And so you see that the green one, those transversal with respect to the motion on the leaves, is essentially 0. We have a positive one. This should go to about 0.9. And then there is a strongly contracting direction. Actually, the sum of the three Lyapunov exponents in this case gives how volumes are behaving. So they are shrinking because this is a dissipative system. If it were a conservative system, you know that the volume would stay the same and maybe just disperse. And we can do something similar to what we have seen for the getting back the other model. We can then set up and let's go for a certain amount of time here. Then we clear trajectory, and now let's suppose that we create a bunch of variation of this condition here, and so going slower, we let them evolve, and you see that the volumes are shrinking, and they start to go in the, you can also say to all of them to put down the pen. So they are going to go. Maybe we have to restart the simulation without the pen because it is too slow. There are too many turtles. So let me go for a certain amount, clear trajectory. Now I create some say 32 or 64 new variations. Then I can let them go. Okay, so maybe too fast. So again, go clear trajectory, pen up, reproduce say to 64, then slower and go. Okay, so you see that they are now following the trajectory, you see, and they are aligning in the direction of motion. And at a certain point, some of them separates. So if you leave them evolve for a long enough time, we again have the same effect that we have seen when we talked about Liouville theorem. In this case, the volume are contracting, but they disperse on the attractor, so that at a certain point, if I take a snapshot, I see essentially them distributed according to some probability distribution on the attractor. Clearly, we can redo this with more pen up, more turtles. Let's try with 128. Go. They start to shrink in the contracting direction. They start to enlarge in the expanding direction. So then some of them start to follow the other wings that we do not see here, but we shall recognize it after some time. And then there is a dispersion on the attractor, and so you see that after some time we can recognize the attractor or simply by looking at where are located all our particles, even though they are not tracking anything. And so essentially, okay, now I asked too much to this system. And so again, we can try to with a larger view from the beginning. Set up, go, clear trajectory, pen up, create a certain number of turtles, go, and now let's stop before enlarging because this is very susceptible. And so we can see now we started a very, very small ball of trajectory, and they stay together for a long time. And but they are still separating at an exponential pace, and at a certain point they will separate all over the attractor, and we shall have a dispersion of all the attractor. Clearly we have to wait a bit, so we let it evolve slightly faster. They start to separate now. Here they are. So separating and mixing. So this is the essence of chaos, which is a continuous separation and folding, separation and folding of the phase space. Okay, and so the essence of chaos is essentially this one. While in fixed point volumes shrink to a certain point, and in the limit cycle they shrink to, say, a one-dimensional object, in three or more dimensions they still shrink in dissipative system, but they are also dispersed along the attraction, and this gives the chaos. And the Lyapunov spectra, so the amount of Lyapunov exponent, mark the behavior of the system. So for instance, in case of quasi-periodic motion, we have 2 0 eigenvalues and the -1. The -1 is responsible for having all trajectory converge to this torus, and the other mark the fact that along the torus there is no exponential separation. Actually, there is also a connection between chaos and fractal dimension. So let's resume quickly the idea of fractal dimension. You may be say, you know the fact that a line is in one dimension, a square is in two dimension, and the cube is in three dimension. But what does this number mean? It means that if you double the length, you double the number of, say, maybe if you want to cover this with an object of a certain size, you may need a certain number of these objects, say balls. But if you halves the size of these balls, you double the number of balls that you need for covering a one-dimensional object. While for two-dimensional object, you have to quadruple the number of balls, and for three-dimensional object you have to multiply it by 8. So to take the cube of this, so not by 8. Yes, the cube of 2 of is 8. And so the idea is that now if you have an irregular shape, you may count how many objects of a given size you need to cover this curve, how this number scales with the size of this object. So, for instance, if you take the Koch curve, which is built in this way, you take a segment, you divide it into 3, you replace this part with the 2 other segments of the same size here, and then you repeat again and again and again. And you may ask how many, say, balls of a given radius you need to cover this curve, and how this number scales with the size. So you see here you may need so in the iteration a certain number here, 4 times of this, then 4 to the certain power, and so on. And so you end up saying that the dimension of the Koch curve is not 1 as a regular cube, but it is larger than 1 and smaller than 2. So it is essentially, you may make a computation here, 1.26. While, for instance, if you can just remove, instead of adding, remove the central part of this segment, so this is the idea of a Cantor set, which is just a dust of dots. And in this case, you have a dimension that is less than 1, it is 0.63. While if you do this in 2 dimensions, say making holes in this Sierpinski gasket, you have something which again is not a surface, not 2, but still greater than 1. So again, you have a fractal dimension. But these are for mathematical objects. So experimentally, how can you compute the fractal dimension? Well, one way is just to count, given your trajectory or your curve, how many boxes you need so it does it touch, and then compute how this number changes with the size of our squares. But this takes a lot of memory for in a computer, because you need a large number of squares, of cubes, or things in the embedding dimension, and most of them are never touched by the trajectory. So the best thing to do is to take a ball at a certain point of your trajectory and count. So not just a ball, but a set of balls of different radii, and then count how many times the trajectory passes through one of these balls. Clearly, it is better to drop these balls from the trajectory, so you are sure that at least some times the trajectory will meet again this ball. And so this is what we can do again with our NetLogo system by opening another version that you have on your system, on the web page of the lesson. And so here it is. Again, we have to arrange this for a better display. So clear again, we can let the system go for a certain time. Then we drop a ball in some point. I don't like this one because it is particular. So let's try again and try to drop this here, for instance, not in a special point. clearly you have to repeat this experiment in several points of the trajectory. So this is the reason for what I didn't like the first choice, because it was very particular with respect to the standard trajectory. And then we can go and compute. We have 4 balls of one of a certain size, one double, and 3 times so square, and 8 times and cube of this dimension, so that in the log scale here they give they are equally spaced. And then I'm counting how many times the trajectory is passing through one of these balls, or all of them. So we can clear the trajectory. You see the point, and at a certain time it may happen that it goes through one of these balls, and clearly by accumulating a lot of numbers, we can have an idea of the fractal dimension of the Lorentz attractor. And so if you wait long enough, or the convergence can be faster and slower, and you have to average over several points, you may end up with a dimension that should be something slightly larger than 2. Clearly, it has to be larger than 2, because otherwise you don't have the possibility of folding. And it is almost 2, because just by watching you see that the attractor has a shape of something which is essentially almost 2-dimensional. We can now try to have more counters, so let's try to drop more counters in different positions, so to have more statistics. It is not so easy to. Okay, now let's try to drop the last one here, let's say, and then we accelerate the computation, maybe without drawing anything here. And then you see that after averaging over a large enough number of points and large enough number of time steps, the number start to converge to something that should be 2.08, 2.1, something like this. 0.05. Clearly, using a system with a bit faster than NetLogo, we have a faster convergence. And okay, so this is a good say simulation, quite old, where you can get the estimate of the number. And another possibility is, instead of following the trajectory, is to take the section. So, for instance, counting only the point where it met the certain reference plane. And so these are called the Poincaré sections, introduced in the beginning of the last century by Poincaré. And you see that if you have a periodic orbit, you have just a few intersections. For quasi-periodic system, you may see a whole line like this, but for chaotic motion, you see something which has a dimension larger than 1. So clearly, since it is a section, we have to leave 1 dimension. So, for instance, for the Lorentz system, here you have a map like this. These are the two wings, and if you look them at a given precision, you may see that this is just slightly larger than 1. But the idea of maps can introduce us to a new subject, which is instead of studying a continuous system that has to be integrated very carefully, why don't we study just a map? So a dynamical system which is defined just by one difference equation. It is not a differential equation, it is a different equation, something that at the times n plus 1, actually this is a plus, it is a function of times at that time, at the present time. This was introduced in the 76 by Robert May, who was studying how insects reproduce, and since clearly at that time the classical approximation was the logistic one that we already have met studying rabbits and sheep, but insects do not reproduce always in a continuous way, but in many cases they lay eggs and then they die, and the eggs hatch at the next, for instance, at the next year, and so it is much better represented by a difference equation with respect to a differential equation. And so he studied a very simple equation that we shall meet in the following slides. But how do we study maps? The idea is that you can draw the map, you can draw the diagonal, so you start from a certain point, you find for instance, in this case, the sinus, or in this case, the cosinus, you find the value for this x, then you have to put this value found here, and the best way is to go to the diagonal, then to go to the function, and so on and so on and so on. For instance, in this case, you see that you have a convergence here, while for this map, the cosinus, you may have an oscillating stable point here. And the advantage of using map is that you may have a lot of interesting behavior, essentially almost what we have already met, just using one-dimensional systems. So it is much simpler to study. So for instance, you see that in this case you have to compare with 1 and not 0 the derivative, because you don't have this 1 plus etc. that we had for continuous time. So you may have a fixed point that are attracting or repelling, and also spiraling fixed point, so contracting, so absorbing and repelling. And okay, so the map that we are going to study is the logistic map defined by these equations. So xn plus 1 is rxn times 1 minus xn, and so we have to replace all these equals to plus, I don't know why. And you may have a fixed point. So let's go to again to NetLogo, and let's see what is going to show here. And so this is our toy system. We can set here the value of, this is called A, but actually it should be R, but the name is not very important. Here I use the NA. And here you can set the initial condition. So when you go, you see the diagonal and the parabola AX1 minus X. And so by changing the value of A, you may see the evolution of the iterations. Clearly, you can start from different initial conditions here. And you see that for A less than 1, there is just one stable fixed point in the origin. Then what happens is that when A is bigger than 1, we still have a fixed point here, but unless we start exactly this point, and now it is unstable, and another one appears here. You see that you converge to this one, and at a certain point, this fixed point is still stable, but becomes spiraling. here, you see, you still have a stable fixed point, but now the approach is spiraling instead of, say, monotonous. At a certain point, this this fixed point becomes, so the attraction becomes slower and slower, and at a certain point, you see that appears a limit cycle. So if you start from a very special initial condition, you see the limit cycle here, ta, 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 ta. And by increasing again the value of A, you may have 2, so a period 2, now it's still period 1, we increase a bit, and now, okay, we have a larger period. Actually, so you see, we have a period 4. Actually, you may have 2 phases. So one is this one and one is the other one. You don't see much difference, but this is the time series. You see the ta 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 ta, or you can go in the other way. So not very different, but they have different phases. And by increasing again, you may have now more complex periodic behavior, and say with 2 different kind of oscillations. Now it is difficult to find the right values of A. So here, for instance, you have a big oscillation and a small oscillation, a big oscillation and a small oscillation, and so on. And at a certain point, you may have chaos. I mean, you may have a regular, like we have seen in the Lorentz system. You start oscillating around some unstable spiraling point, and then you have a broad oscillation. Then you start again oscillating around this point, and then again oscillation. And here you may also use the histogram of values of the map in order to have an idea of what is going on. Clearly, for a fixed point, except some transient, so you may go to very large time series, except for the transient, you have just 1 point. When you have the appearance of a limit cycle, you have 2 points here, two values. Then by increasing again A, you may have, okay, here you have 4 values, it means a period 4. And then you may have other period 8, and then you have chaos. Chaos is given by some continuous dispersion of values. And finally, clearly, you still within chaos, you may have some periodic window. In this case, you have period 3 here, you see, just surrounded by chaos in several positions. And finally, for A equals 4, which is the maximum value, you have here a very broad distribution of values. And clearly, you can perform, since the map is very simple, you may perform by hand a lot of computations, and you can compute analytically or approximate the threshold for the chaos. And what the nice plot that takes into consideration all values is this one that I can also show live. So the idea is to have to simulate the system for all possible values of A from 0 to 4. For each values of A, we let the system evolve for a long time so that we throw away a certain transient, and then we can plot a certain number, say 300 or 400 dots here. So for instance, you see that here is what is going on. So for these values you see here, for these values of a up to 1, you have just a fixed point in 0. Here you have a first bifurcation, so this point becomes unstable, and this is and another stable point appears. This is a transcritical bifurcation. Then you have a period doubling, so essentially a hop bifurcation from a stable fixed point to a limit cycle. That is now, in this case, only just oscillation. Then you have other bifurcations for the period doubling. We can also zoom here, and you see that this bifurcation is actually very similar to the one that we have seen. So it is a kind of hop bifurcation from period 2, this is just one branch, to period 4, and then to period 8, and then again. And at a certain point, you have the chaos. And you can see that actually chaos here in this region is still with substructure, because this branch here and this branch here are just separated by an oscillation. So this first bifurcation that gives a period of oscillation maintains, since for instance in this case you have one dot here, then one here, one here, and one here, and again. So if we examine what happens in this region, you have all these bifurcations, but you see here essentially the oscillation is from one point here and one point in this branch, one point here, one point in this branch, until at this point you have the mixing of the two attractors. You still see that there are structures, and these white stripes are the periodic window. So at a certain point we again see a periodic window, and then again a bifurcation. And what is interesting is that inside, when you enlarge one of these small pieces, you again see something which is very similar to the original situation. And this is a classical say sign of a fractal structure, because it is invariant, and you see again and again the same figure. And if you perform the computation of the Lyapunov exponent, which is marked below, you see again a lot of information. So the Lyapunov exponent is negative or 0 in all when there are fixed point or limit cycles. But you see that actually here you have here the bifurcation that corresponds to 0 Lyapunov exponent, because nearby this point you have essentially a part, a position here where the space is locally flat, so you don't have a dominant contraction direction, and this is reflected by the fact that the Lyapunov exponent is going to 0. Another important point is still where there are fixed point is here, where the Lyapunov exponent goes to minus infinity and then increases again, still being negative. And this corresponds to the transition from convergence towards, in a monotonic way, to spiraling. So this transition here marks the point where points start to spiral near, so towards the fixed point. Then again, Lyapunov equal 0 marks the bifurcation, and then again here you have a change of, say, monotonous to spiraling. It is anticipating this new bifurcation here, and so on and so on. And then when the trajectory becomes chaotic, this is marked by the fact that the Lyapunov exponent becomes larger than 0, while all these periodic windows are marked by the fact that the Lyapunov exponent becomes again less than 0. So if you enlarge this region, you will see a positive Lyapunov exponent that suddenly becomes negative. Then again you have a change of say convergence, and then bifurcations here, and another bifurcation, and then comes again the Lyapunov exponent becomes positive. And so you may study a lot about chaos just using these very simple logistic map or other maps. So we have a lot of phenomenology, and you can also analyze a lot of things by hand. You see the Hopf bifurcation, the unstable separatrix here, and you see that the period doubling bifurcation is actually bifurcations that occurs for the double iterated map, because clearly when you go from period 2 to period 4, if you iterate the map twice, you see just a bifurcation from a fixed point to a period 2. And near the periodic windows here, if you go from larger values of A to slower one, you have something that resembles the infinite period bifurcation that we have seen in the lesson before, because you have this for instance, this double or triple iterated map that becomes tangent to this line, so that you have this point that stays for a long time near here and then goes another way. And so this is called also intermittent, because you see what happens. It has this infinite period here, and then again very long transient here, then it goes away, so that you see these intermittency. So you have almost regular behavior, then suddenly burst of chaos, and then again this oscillation here, which essentially is something similar to what we have seen when we studied the infinite period map transition. And okay, so there are a lot of interesting points, and this is a very nice plot with music of what is going on in the logistic map. So now we are going to zoom inside some point of the logistic map with a very high resolution. It means very long computation, and you may appreciate the fact that when you go deep inside some point, you again and again see the same structure and the same periodic window and so on. So this is a typical signature of a fractal. I stop here. And clearly, for a given value of A, you can compute the fractal dimension using the same technique, and you find a certain number which is not, it's like the Cantor set. It is not just a set of points, but it is not a continuous surface. This is just a quick introduction to the subject. Clearly, if you look, say, for instance, on on Google, you may find millions of articles and pages devoted to chaos and so on. So this is just a gentle introduction to the subject, and then we move to other subjects. That's enough for this lesson, and see you again.